In this video, I'm going to go over AP Calculus using accumulation functions and definite integrals in applied contexts. So we're looking at real-life situations and how we can use integrals and derivatives and all that good stuff to answer various problems. So our first scenario, a customer at a gas station is pumping gasoline into a gas tank. The rate of flow of the gasoline is modeled by a differentiable function f, where f is measured in gallons per second and is measured in seconds since pumping began. Selected values of f of t, our rate, are given in the table above. So part A, using correct units, interpret the meaning of the integral from 60 to 135 in the context of the problem. Then we're going to use a right-Riemann sum with 3 subintervals, and they've given us the intervals to approximate that integral. Okay, so our interpretation. If f of t is the rate at which we are pumping in the gas, then the integral is going to be the number of gallons pumped into the gas tank from t equals 60 to t equals 135. Now we're going to do the right-Riemann sum. So we're approximating, and we want to be careful with this notation because sometimes I'll see people like do the integral symbol and then just start doing the Riemann sum, but we're approximating this using our Riemann sum. Okay, so we're going from 60 to 90, 90 to 120, and 120 to 135. So I'm just going to do 90 minus 60. That's going to be the width of my rectangle. The height we're evaluating on the right side. So we'll be evaluating at 0.15. My next width is going to go from 120 to 90. And then its height will be 0.1. And then our last one is 135 minus 120. On the right side is 0.05. This is a calculator active question, but you can leave your answer just like that. That can be put into a scientific calculator, but if you did type it into your calculator, you get 8.25 gallons. Okay, part B. Must there exist a value of c for 60 to 120 such that the derivative equals 0? Well, this is talking about the mean value theorem. So what I'm going to do is find the difference quotient of f of 120 minus f of 60 over 120 minus 60. From the table, both 120 and 160 are 0.1. So that equals 0. So must there be a value of c where the derivative equals 0? Yes. Okay. And the way we're going to justify this is since we have to prove the hypothesis of the mean value theorem. So since f of t is differentiable, f of t is continuous. Because if it's differentiable, then it had to be continuous for that to happen. So by the mean value theorem, and I am going to abbreviate MVT, and I'm basically just going to mimic this back. Okay, so just taking the wording straight from the problem, by the MVT, there must exist a value c for 60 is less than c is less than 120, such that f prime of c equals 0. Okay, next, the rate of flow in gallons per second can also be modeled by this equation for 0 to 150. Using this model, find the average rate of flow of gasoline over the time interval 0 to 150. Show the setup for our calculations. Okay, well, the average value, so if this is giving us the rate and we want to know the average rate, we're finding the average value of a function. So we're going to have 1 over 150 minus 0, and then the integral from 0 to 150 of g of t dt. That's the setup for my calculations. Now we're going to let the calculator do the work for us. I'm going to go ahead and put this into my y equals. And keep in mind you can do this in Desmos, but I'm doing this on a TI-84. Okay, so I've typed my the equation into the y1 of my calculator, and then I'm going to go ahead and do this calculation. So I've got 1 over 150 times the integral from 0 to 150 of that equation that I stored in y1. And our value to 3 decimal places, I'll even give some bonus decimals, so 0.9599. As long as you're accurate to 3, you are good to go. The last part of this problem, using the model G that we just did, find the value of G prime of 140, and then we're going to interpret the meaning in the context of the problem. So first up, we're going to go ahead and take the derivative. Let the calculator do this. Okay. We stored it in y1, so we'll do our derivative of y1 evaluated at 140. Okay. So we get a negative 0.0049. Okay, then we want to interpret this. So this is the rate of change of G. So if G is gallons per second, it's the rate at which that is changing. So the rate of flow now here's where you have options. You can say is changing at a rate of this, or you can say since this is negative, the rate of flow is decreasing. Change is kind of a safe way to say it. But if I attach that decreasing, I don't include the negative when I'm explaining, because that negative is implied. So it's decreasing by this. My units are going to be gallons per second. So the units here are gallons per second, and it's the rate at which that is changing. And then we want to be specific at time t equals 140. All right, our next problem. From 5 a.m. to 10 a.m., the rate at which vehicles arrive at a certain toll plaza is given by this guy here, where t is the number of hours after 5 a.m. And A of t is measured in vehicles per hour. Traffic is flowing smoothly at 5 a.m. and there are no vehicles waiting in line. So first, write but do not evaluate an integral expression that gives the total number of vehicles that arrive in the toll plaza from t equals 1 to t equals 5. We got our integral. My limits of integration are going to be 1 to 5, and we just want to integrate our function. So that's a pretty darn easy question. Next, find the average value of the rate in vehicles per hour at which the vehicle arrives in the toll plaza from 6 a.m. to 10 a.m. So I'm going to go ahead and type this into my calculator again, into the y equals. Okay, and then we want the average value again. So this is the same as the last question. It's going to be 1 over 5 minus 1 times the integral from 1 to 5 of our rate. So we'll let the calculator do the work for us again. So we've got 1 over 4. I can go ahead and do that mental math. Times the integral from 1 to 5 of that function I stored in y1. Okay. So we get 375.5369 just for fun. This is the rate at which the cars, so this is our average rate in cars per hour. It didn't ask for the units, but it doesn't hurt. All right. Next, is the rate at which the vehicles arrive at the toll plaza increasing or decreasing? So if we're trying to find increasing or decreasing, we want the derivative. So I'm going to find the derivative of our rate function at 1. and we get 148.947. So is it increasing or decreasing? It will be increasing. Because a prime of 1 is greater than 0. Okay, last part of this question. A line forms whenever A of t is greater than or equal to 400. The number of vehicles in the line for t from A to 4 is given by n of t equals the integral from A to t of A of x minus 400, where A, this one, is the time when the line first starts to form. To the nearest whole number, find the greatest number of vehicles in the line in the toll plaza on the interval A to 4. So this is going to be an extreme value problem. Okay, when you're trying to find the greatest on a closed interval, we want to do what's called the candidates test, where we're going to check the endpoints and we're going to check the critical points. Now, you may be able to eliminate some that are potential minimums, but I think it's just safe. Check all of those values and you've covered your basis. Okay, so the first thing I'm going to do is take this derivative. It's actually going to serve two purposes in this case. Because if I take this derivative, we get A of t minus 400, because the derivative of an integral, they're opposite operations, so they cancel each other out. So we want to know when this equals 0 for really two different reasons. One, because I need to find this value of A, which is the first time that the line begins to form, which what happens when our A function is equal to 400. And then it also covers our basis on our critical points. So I've got my function here. I'm going to go ahead and put 400. For my window, I'm going to go from 0 to 4, because that's my end of my interval, so I don't really care about other values. For my y values, I need to be able to see 400. So I'm just going to go from like 0 to, let's do 600. And then we'll graph. So there's our rate function. And there's 400. So these two values are what I'm interested in. This first one is A, little a. So we're going to calculate the intersection. Okay. So our first one, A, is going to be 1.469317. Now what I'm going to do is I'm going to get out of this without touching anything, and I'm going to store, so if I hit do X and store it in A. Okay, so that value that I found, it's automatically stored in your X value. So that's what we're using there. So now that's stored in A. Let's go back to the graph and find our second point. Now we want our other point. Okay, and what I'm going to do is I'm going to call that B. But I'm going to go ahead and get right out of here without touching anything and store X in B. So I have those two values stored with lots of decimals. Okay. Now, I'm going to make a table here. Okay, to get to my candidates. So my first candidate is A, and you can write the whole thing, but since I've identified that that's what A is, we can just leave it. I want A, B, which is a critical value, and 4, which is an endpoint. And what we're going to do is plug it into this equation here. Okay, if I plug in n of A, we have the integral from A to A of ax. Doesn't really matter what I'm integrating here, because the integral from A to A is just going to be 0. Now we're going to do n of b, which will be the integral from my a value to my v value of our function. Okay, and then we're also going to check 4. Okay, so those are this one we already set is 0. We'll go ahead and calculate the other 2. So we've got the integral from, literally we're going to type in the letter a because that's where I stored it, to b, because that's where I stored that, of my y1 minus 400. Okay, and this gives me 71.254. Go ahead and put that in my chart. 71. Okay, then just to save myself some time, I'm going to go up and snag that because the only thing I want to change is from that B, swap it out for a 4. So we get 62.338. So the greatest number, our candidates are the 2 endpoints and our critical point. This one happened at the critical point. So the greatest number of vehicles to the nearest whole number would be 71. All right, so the last problem I'm going to go through, when a certain grocery store opens, it has 50 pounds of bananas on a display table. Customers remove bananas on the display with this function. The time is from 0 to 12, where f of t is measured in pounds per hour and the number of hours after the store has opened. It's important to highlight that we start with 50. Okay, and then people come in and take the bananas. After the store has been open for 3 hours, store employees add bananas to the display at a rate modeled by this guy. Note that it starts at 3 because it doesn't happen until hour 3. This is also measured in pounds per hour from when the store opened. So how many pounds of bananas are removed from the display table during the first 2 hours that the store is open? So I'm going to store this in my y1 and I'm going to store this in my y2, and then we will answer that question. So how many are removed? Well, that's going to be the integral from 0 to 2 of our f of t dt. And again, we just let the calculator do it. I stored that one in y1 and the second one in y2. So we are integrating from 0 to 2 of y1 dx. So how many pounds? There is 20.051 pounds are removed. Okay, find f prime of 7. Using correct units, we're going to explain the meaning. So we're going to do the derivative of y1 when x is 7. Okay, so f prime of 7 is a negative 8.1195. Okay, so this is the rate of change of our function. So we've done one similar already. The rate that bananas are removed. And again, you can say is changing by negative 8.1159, or we can say is decreasing, because it is negative, by 8.1195 bananas per hour. So it's the rate of change of our rate. Okay, again, you can say changing by negative, and that would be equivalent. I think then just decreasing is a little bit more specific, but we do have to drop that negative and be a little bit deliberate with that. C says, is the number of pounds of banana on the display increasing or decreasing at t equals 5? Well, what I'm going to look at is the rate going in, and I'm going to look at the rate going out. Okay, so plugging into my calculator, I've stored these in Y1 and Y2. So I want Y1 at 5, and I want Y2 at 5. Okay, well, the rate that they're being removed is 13.7959. The rate at which they're being added is 11.5328. So if the rate of people taking the bananas is bigger than the rate of people adding bananas, the number of bananas is going to be decreasing. So put that in words. Using is the number of bananas. I'm going to say the number of pounds of bananas is decreasing because f of 5 is greater than g of 5. Last one, how many pounds of bananas are on the display table at t equals 8? Well, we have 3 things to consider. We have how many we started with, which was 50. Okay, how many are being removed? So at t equals 8, they're being removed from 0 to 8, and we're using f of t. But we have these nice grocery workers who are adding bananas, but they don't start until 3. Okay, so you could enter it all in separately, or you can let your calculator do all of this for you. What we get is 23.347 pounds. So that was different real life examples with accumulation functions.